In this video, we're going to take a look at an introduction to a topic called discrete random variables. Essentially, when we first see these questions, they can be quite abstract, and it takes a bit of time just to get used to the notation. But the key is in the title, discrete. So when we're working with discrete data, it's whole numbered values. It's going to occur at random. So imagine a nice way that I always visualize with these questions, just to start with, right? If it gives it in a table like this, essentially what this is saying is the variable that we're working with is r in the question. And the only possible outcomes that r could ever take are these discrete values. So r could equal 1, r could equal 2, r could equal 4, or r could equal 8. So if you just try and visualize, you've got like a spinner, and there's 4 outcomes on that spinner. Okay, you could get a 1, you could get a 2, you could get a 4, or you could get an 8. But this is not like a fair spinner, like it's not equally distributed, so the chance of you getting a 1 and a 4 is not the same. And if you think about this, we already know some of the outcomes, so whatever the spinner looks like, if I spin it, the chance of it landing on a 2 would be 0.1, so it's about 10% chance of me getting a 2 as an outcome. Chance of me getting an 8 would be 0.3. So obviously we're gonna, if we kept spinning this spinner and recording the results, I definitely expect to get more 8s than I would 2s. Okay, but obviously it doesn't give us a context. It just says here's a discrete distribution, puts it in a table. But quite often when we get into the exam style questions, it will have like a context, which makes it a bit easier to visualize. But for now, we're going to just look at like the rules for this distribution before we get stuck into the exam style questions. Okay, so we know that there's only 4 possible outcomes. We could get 1, 2, 4, or 8. We know these are the associated probabilities. That's what this notation means, the probability of me getting this event. So these are capital R to stand for like the whole distribution, and the lowercase r is just like one event, so one outcome within the distribution. So if you want to find the value of Q, you definitely want to highlight this in your notes. Like, you know that the probability, if it gives it to you in a table like this, and because the discrete distribution, there's only these possible outcomes, the probabilities will always sum to 1. And that should be pretty obvious if you think about it. Like, when you spin the spinner, there's only those 4 possible outcomes. So the combination of those events represent this entire distribution. Okay, so we know that Q plus 0.1 plus 2Q plus 0.3 must equal 1. 3Q would equal 0.6. So Q must equal 0.2. And once we've got that, I mean, we could probably fill in the distribution, the probabilities, to help us with the rest of the question. So 0.2 and 0.4, and just check. Like, they do add up to 1, don't they? Okay. Then after that, it's actually just a question of a couple of probability questions for now. There is more theory on this, but we'll see that in later videos. Okay, so we want to find the probability that R is, so imagine we spin the spinner, what's the probability that the outcome is greater than or equal to 2? So if it's greater than or equal to 2, it could land on a 2, it could land on a 4, or it could land on an 8. And obviously I'm using the word or, but clearly I think it must be hopefully quite intuitive that if it's 2, 4, or 8, it's these probabilities that we add up, isn't it? Another way of thinking about it, if it's greater than or equal to 2, it's not 1, is it? Sometimes, like, if there's like a large amount of outcomes, if you can narrow it down to like, oh, it's not this one, it's easier than adding up those. But if it's not 0.2, it is these. And we could literally just write down, I mean, I'll show the calculation, 0.1 plus 0.4 plus 0.3, or you could think about it as 1 minus 0.2. Either way, we're going to get 0.8. Okay. With this one, it might be the first time you've seen does not equal. Like, probability of an event like not equaling something is 1 minus the probability that it does equal. So if you ever get like a not equal to, I always think about, well, if it's not equal to 2, what's the probability that it is 2? The probability it is 2 is 0.1. So obviously not 2 would be everything else. So you could think about it as one minus the probability that it does equal 2, r, which would be 1 minus 0.1, 0.9. The next part of the video is a little bit wordy, so let's just read through this carefully. It says, a random sample of 3 numbers are selected from the distribution. So think about now, right, if we've got our spinner, if we spin it 3 times, and then we get out an event, or the outcome, so we could spin it, it could land on 1, spin it again, it could land on 1 again, spin it again, it could land on 1, but obviously there's lots of possible combinations. And what we're being asked is like a specific situation when we do spin it 3 times. Okay, so a random sample of 3 is taken and calculate the probability that all are even. Okay, so if they're all even, first of all, let's just think about like what's the probability that it's even. Like if you spin it once, what's the probability of it being even? And the outcome could be 2, 4 or 8 because they would be even numbers that it could land on. So the probability of it being even would be 0.8. Okay, and you can sort of visualize this as a tree diagram, like it's either even or it's odd. Probability of being even is 0.8, probability of being odd is 0.2. And what we're looking for is, this happens, it's spun 3 times, or it's even every time, so it's even, and then it's even again, and then it's even again. And notice I'm using the word and now, like even, and even, and even. If this event happens 3 times, please do not multiply it by 3, which is sometimes what some of my students say, because that'll give you a number bigger than 1, and you've broken probability, you've broken maths. Like that event happens these 3 times, would be the probability of it being even cubed. So that would be 0.8 cubed. And that would give us 0.512. There's a good chance, just over a 50% chance. And I think about it, that's because like the probability of it landing on an even is quite high, isn't it? So the chance that happens 3 times in a row, it's fairly likely that would happen. Okay. If we want 8 to appear once for the next time, we've got to think about this carefully. Okay. It's not just as simple as saying, well, the probability that 8 appears is 0.3. It's not just going to be 0.3. We're spinning it 3 times and we want 8 to appear once, only once. So basically what we want to happen is we want 8 and then not 8 and then not 8. And a lot of students would lose marks on this question because if you think about that, you're not thinking about the whole picture. Okay, if I do this calculation, I'll show you what that would look like. So the probability of 8 would be 0.3, not 8 would be 0.7, not 8 would be 0.7. And it looks like, it might feel like that's the correct thing to do, and you think you're getting full marks on this question, but you've missed the key point here. What I've calculated there, if I do that number, is I've calculated the probability that I get an 8 first, and then I get not an 8, and then I get not an 8. You got to think about the number of combinations that this could happen. Like if you're spinning it 3 times and 8 appears once, you could have, if I just use A and B, like the 8 could appear and then it not appear, or you could, first roll would be not an 8, and then you could get an 8, and then it'd be not an 8 again, or you could do not an 8, and then you get an 8. In other words, like there's 3 times that could happen. And we could write the calculation out 3 times, like it could be 0.3, 0.7, 0.7, and then it'd be 0.7, 0.3, 0.7, and then or, like I'm adding this up, because if you think about if you went along the tree diagram, it'd be that combination or that combination. Okay, or then you could get 0.7, 0.7, and 0.3. But like a quick way of doing this, because you realise that like because the order just changed around, like that number would be the same as that number, which would be the same as that number. You could just do 0.3 times 0.7 times 0.7 and multiply by the number of combinations. Like it could happen 3 times, so just times it by 3. Okay, and let's see what that gives us. Okay, so I've just used my calculator and I'm getting 0.441. You could check if you want to add those up, it would still give you the same answer, 0.441. Alright, so it's the same as multiplying it 3 times. Okay, let's try another example. Next example is set out slightly differently, and this might be the first time we've seen this notation before. Okay, so what it's saying is the probability that of our outcome, in this case we're using the variable x, probability of the outcome is equal to k times x squared when x is equal to 1, 2, 3, 4 or 5. Now clearly we're working with a discrete random variable here, because what this is telling us is that like this thing here represents the number of outcomes, the outcomes that we can get. So imagine if we had a spinner again, like we could land on a 1, we could land on a 2, we could land on a 3, we could land on a 4, or we could land on a 5. But the probability of any other outcome, like say, what's the probability to get 6, what's the probability to get 2.7, is 0 for any other number. So there are only 5 possible outcomes, and they are all these discrete values here. Okay. So chance of me getting anything else apart from 1, 2, 3, 4, or 5 would be 0. And the first thing we'd have to do is find the value of k. Now again, another thing that you want to highlight in your notes here, if it's not given to us in the question, I would strongly recommend, for most exam questions I've seen, form a table just to begin, because it makes it a lot easier for what's going to come next. Okay. So the table is going to look like this. Like at the top we list our possible outcomes, so the distribution could be 1, 2, 3, 4 or 5, and then the associated probabilities. Now if you look at this, the probability is a function of x, so the actual chance of the outcome depends on the probability of the outcome happening depends on the number itself. So the chance of me getting a 1 would be k times by 1 squared, which would be k. The chance of me getting a 2, the probability of me getting a 2, would be k times by 2 squared, which would be 4k. Probability of a 3 happening would be 9k. Probability of 4 would be 16. And the probability of 5 would be 25. Okay. Now once we put it into the table, remember what we know about this distribution. Like the spinner is only ever going to land on a 1, 2, 3, 4 or 5. In other words, we know that the probability of all of the possible outcomes will always add up to 1. Okay. So k plus 4k plus 9k plus 16k plus 25k must equal 1. Okay, so that would give us 14k, k, 50, I think it's 55k equals 1, so k would equal 1 over 55. Okay, so once we know the value of k, it might be useful to write these out again. So the probability of me getting a 1 would be 1 over 55. Probability of me getting a 2 would be 4 over 55, and so on. All right, I'm not going to just for now, because we can leave it as we go, work it out as we go. Say the probability that x is less than 3. Okay. And just think about it, well, what outcomes are less than 3? Not less than or equal to 3, less than 3. So it can't be 3, it's got to be less than 3. So it could be 1 or 2. Which would be 1 over 55 plus 4 over 55. Which would be 1 over 11. Or 5 over 55, which you can simplify down. Okay. Next one. Probability of the outcome being less than 2.5. Now obviously, I mean, these values, you could only get a 1, 2, 3, 4, or 5. Like 2.5 would be somewhere in here. the chance of me getting a 2.5 would be 0, but the chance of it being less than 2.5 is still the same as the chance of it being less than 3. Like any value here, less than 3, less than 2.5, these are the only two outcomes, isn't it? Okay, so that would also be 1 over 11. Next one, probably to be more than 2.5 would be that way, wouldn't it? So it's either less than 2.5 or it's more than 2.5. Technically, it's like there might be a situation where it's if we wanted to include all possible outcomes, it'd be less than 2.5, greater than or equal to 2.5. But because in this question, like it can't equal 2.5, like it's either less than 2.5 or it's more than 2.5. It's never equal to 2.5 anyway, is it? So more than 2.5 would be this, or this, which we could add up. We want this one, or this one. But basically we don't want those ones, and I already know what they were, so I'm just going to do 1 minus the other ones. And quick calculation, you can get 10 over 11. Okay. Next part says probability is less than or equal to 4. So obviously less than or equal to 4, we can include the 4. So it'd be 1, 2, 3, or 4. We could add up these. Or we can see it's this one that is the one that we don't want. So it'd be 1 minus this one, which we could write as 30 out of 55, which would simplify down. Obviously you can use your calculator in the test anyway. You could simplify this down. Both multiples of 5, so we could write it as 6 over 11. Okay. The last part is quite a tricky part, guys, but I put it on there because I thought it'd be nice for us to look at. We will practice more of these given questions in case they come up. They haven't really been coming up in recent papers, but they used to ask them a lot on the old exam. So let's have a look at what this one's asking. Okay, so first thing we've got to think about this notation. And what this is saying, like, is the probability that this happens given, like I would read that as given that. So the probability that x is less than 3, given that, we already know that x is more than 1. Okay, so if you think about the formula for this, it's the same probability that x is less than 3 and x is more than 1. When you're given something that happens, like we're not looking at it, it's like limited our options. It's not like we're not looking at the whole world that adds up to 1. Like it couldn't be a 1, 2, 3, 4, or 5. Like we already know that x was more than 1. So like the way that we can adapt that is we divide by the probability of it being more than 1. Like we know x was more than 1. Don't do this in the exam, but I'm gonna draw on this because it's the last part of the question. We already know this. Like, okay, so imagine you've spun your spinner and you know that x was more than 1. Okay, so we definitely can, so that we can discount that scenario. We know that's not happened. We know for a fact that x was more than 1. Okay, so we're not working in, like, all of these probabilities we could have divided by 1 because they all added up to 1, but now the probabilities add up to this world where x was more than 1. Okay, probability that x is more than 1 is 54 out of 55. Like that's the world that we're working in now. Like we know it was more than 1, so now out of these probabilities, given that it was more than 1, what's the probability that's less than 3? Okay, so we know it was more than 1. Now we want to say what's the probability of being less than 3. So in this world, which ones are less than 3? Well, it's this one, isn't it? It's like the 4 out of 55 out of the world where we knew something had already happened. Anyway, and we can think about it using the formula, but try and get a feel for it as well. Like, if I'm saying that this given this is the same as this and this divided by this, what does that even mean? We want x to be less than 3 and x to be more than 1. Like, it's a bit of a weird way for me to write it, but you want it to be more than 1 and you want it to be less than 3. In other words, you want it to be this. Like, that's the only situation, isn't it? So this happened out of this world where we knew something else had already happened. So that would give us 4 out of 54, which we could simplify down to 2 out of 27. Okay. Nice one, guys.